Hello, and welcome back. This is Chapter 4, Video 7, where we'll be talking about the basics of the SDE derivation system. The next video, we'll talk about some strategies for using SDE. Okay, so first let's quickly talk about what SDE is. You'll remember that SDE is our sentential derivation system, the 11 basic rules that allow us to do all and only those derivations that can be correctly done. We don't actually need any more than SD to do derivations. However, we are going to extend our derivation system to SDE, for sentential derivations extended. This includes all 11 rules of SD, so we still have those original rules to use, but we add 3 new inference rules and 10 new replacement rules. And replacement rules are sometimes called equivalence rules or substitution rules. Now, this new system, SDE, is a conservative extension of SD. That is, in SDE, we can do all and only the same derivations that we could do in SD alone. There's no more power. That's what makes it conservative. But we can do many of those same derivations much more simply and efficiently. The extended system makes derivations easier by giving us some shortcut rules and some ways of manipulating formulas that will make things more efficient. As our first example, take this derivation. Now, as you'll remember from doing SD derivations, since we have hook D as our goal, we can insert that down at the bottom because we're going to work from the bottom up. Since the main operator of our goal is a hook, we're likely going to do a hook introduction, which means assuming D, the thing that we want to attach the hook to, and trying to get some sort of contradiction in the course of that subderivation. You probably see this is not a terribly complex derivation, but with 1 and 3 and arrow elimination, I can get G. That's actually going to be my Q. And then I can simply reiterate line 2 into the subderivation to get my not Q. And I've got a contradiction. That allows me to exit the subderivation and claim 3 through 5 hook introduction to get the D. Now, this isn't terribly complex, but this sort of inference where we have a conditional and then the negation of the consequent in order to get the negation of the antecedent, this occurs very frequently. So it would be nice to have a rule that allows us to do it more directly. And in fact, we have such a rule. This rule is the MT rule, or modus tollens. What it tells us is that you have a conditional, whether it's a simple or complex conditional, as long as it's got an antecedent and a consequent. And if you have something matching the consequent but with a hook attached, then you can derive something matching the antecedent but with a hook attached. And it mimics the inference. If P, then Q, but not Q, therefore not P. So the derivation on the left could have been done in one step like this. Since 1 is a conditional and 2 is the negation of the consequent, we can derive the negation of the antecedent directly. And we cite 1, 2, modus tollens. Now, we'll talk more in the next video about strategies for using these rules. I want to introduce the other 2 inference rules. Take this quick example. Suppose we have 2 conditionals, A arrow B and B arrow C. We can easily derive from these A arrow C. In SD, without our new extended rules, this is going to require a subderivation. Put A arrow C in as the goal, and since the arrow is the main operator, that strongly suggests we set up a subderivation with A as the auxiliary assumption of the subderivation and C, the consequent of the conditional we want, as the goal of the subderivation. Now it's actually just 2 steps to get there. With 1 and 3, we can get B by arrow elimination, And then with 2 and 4, we can get C by arrow elimination. And that quick little subderivation, of course, 3 through 5, gives us A arrow C by arrow introduction. But again, this is such a natural and familiar pattern of inference, and a useful one, that it might be nice to have a shortcut rule for it. And we do. That shortcut rule is called hypothetical syllogism, or HS. You have two conditionals where the consequent of one matches the antecedent of another, and we chain them together and drop out the middle to get from the antecedent of one to the consequent of the other. So it's called a hypothetical syllogism because it involves conditionals or hypotheticals, and a syllogism because it's a simple two-premise argument. So the derivation on the left here would be very quick. We go straight from 1 and 2 to the goal, A arrow C, and we cite 1, 2, hypothetical syllogism. Doesn't save you a lot of work, but it saves you a subderivation, and it's a nice familiar sort of inference. Now consider this derivation. This is one of the more difficult derivations to do in SD. So the new SDE rule we're about to introduce is actually going to save us a lot of time. But let's look at the way it has to be done in SD. Given this function in line 1, I have to do a V elimination in order to complete this problem. I need to show that both sides of that expression go to my goal B. So set this up. You may remember that I'm doing one of these. So very short subderivation involves assuming one side of this function and reiterating that side. Let's go to the other side of the iteration. One where we have the iteration in another line. Then we assume the iteration of our subgoal. And now we reiterate line 2 and line 5. I reiterate line 5 first. So that function is line 7 a. Last we remove the hook from my function 6, which is line 9, using B 6 through 8 for elimination. And now, since I've shown in 3 to 4 that D leads to D, and I've shown in 5 through 9 that D leads to D, then my order elimination involving this function line 1, I get D. Again, this is very complicated to do in SD, but it's really a rather intuitive inference. All that we're doing is saying, hey, it's either B or D, but it's not D, so B is the result. Despite how intuitive that is, in SD, it actually takes a long time to do. But since we know whenever we have a disjunction and the negation of one of the disjuncts that we could do this, we can give ourselves a shortcut rule. And this is that shortcut rule. It's called DS, or disjunctive syllogism. Again, it's a syllogism because it's a simple two-premise argument, and it involves a disjunction. Now, there's actually two versions of this rule, just depending on whether we have the negation of the left disjunct or the right disjunct. Right? So if you've got a disjunction and then the negation of one of those disjuncts, you can derive the other disjunct. And of course, it works if you have the negation of the right-hand disjunct. You get the left-hand disjunct as well. So that 10-line derivation that we just did becomes this. We get it done in a single step. 1, 2, disjunctive syllogism. And you'll note that we're using the right-hand side version of the rule. Nice and simple. Now, the 3 new inference rules that we've introduced really do help make things simpler and more efficient. But the real power of SDE comes in with the replacement rules. Before I describe exactly what distinguishes replacement rules from the rules we've seen so far, let's take a look at an example. Now, this is a pretty simple derivation. We just need to derive D from lines 1 and 2. And D sits in the consequent of line 2. So it would be nice if we had something to match the antecedent of line 2, and a simple arrow elimination would give us the D. The problem is what we have in line 1 does not match the antecedent of line 2. And with the rules we have now, the original 11 plus the 3 new inference rules, the only thing we can do is take line 1 apart with wedge elimination and put it back together in the proper order with wedge introduction, like this. Now in line 5, we have a formula that exactly matches the antecedent of line 2. So 2 and 5 together will give us the D. Now this is a little bit annoying because we're smart enough to know that while these two formulas are not syntactically equivalent, they are semantically equivalent. So why can't we just use 1 and 2 together to get at D? Well, we really just said why. Derivations are a syntactical system, not a semantic system. So we need the syntax to match exactly. That's why we have to take the steps in line 3, 4, and 5 to get the matching subformula. But what if there were a way to just skip these steps? Since we know of the equivalence, it would be nice to have a rule that exploits that equivalence and allows us to do this derivation much more quickly. And in fact, we have such a rule. That rule is called commutivity or commutation, and we'll abbreviate it COM. What this rule tells us is that whenever we have a conjunction or a disjunction, we can replace it with the same conjunction in the opposite order, or the same disjunction in the opposite order. So in the case of the derivation over here on the left, with the new COM rule, we can do it this way. Looking at line 1, it is not in the correct order to exactly match the antecedent of line 2. The commutation rule involving the wedge allows us to take line 1 and just rewrite it in the other order. We cite line 1, COM. Now, line 3 exactly matches the antecedent of line 2, so we can do the arrow elimination. And it saves us a lot of time in a couple of steps. Now, that's actually just one way we could use the commutation rule here. We took a whole line and we applied commutation to it to switch the order of the main subcomponents of that line. But the great thing about our replacement rules is that they allow us to work on subparts of lines. Let me illustrate what I mean. So same derivation again. This time, instead of applying COM to line 1, we're going to apply COM to just this interior part of line 2. That's what it means to say that replacement rules can operate on the well-formed subparts of formulas. So we'll take line 2. This part of it is going to stay as is, and then we'll take the B wedge A in the interior of those parentheses and flip it to A wedge B. So this is 2 commutation, slightly different from what we did on the left, but equally as valid. Now, line 1 matches the antecedent of line 3, so our justification in arriving at D in line 4 is 1, 3, arrow elimination. So it's not a big deal for this simple derivation, but that ability for us to affect interior parts of lines is going to be a game changer for certain complicated derivations. I'll show one last example with commutation and then introduce the rest of the rules. Now take a look at this derivation. Our goal is to get A, arrow, not E, wedge, D. Now one of the strategy points that comes up with SDE is the following. We don't actually need the SDE rules to complete this derivation, but it will make it a lot easier. We still want to engage in goal analysis, but we want to look for patterns where we can employ our new shortcut or replacement rules. So for example, here I'm trying to prove a conditional, and that suggests arrow introduction. But don't forget, I also have hypothetical syllogism. So that might work too. In fact, I notice that the consequent of line 1 is almost the same as the antecedent of line 2. Given now that I have the commutation rule, I might be able to use it to set up a hypothetical syllogism, in which case I would avoid the arrow introduction subderivation altogether. Let's try that. So it doesn't matter whether we alter line 1 or line 2. What we're going to be doing is addressing one of those two areas underlined in orange. So that I don't have to write out the longer formula, I'm going to deal with line 1. So we just flip the order of the disjunction in those parentheses, and that is 1 commutation. Now I can do a hypothetical syllogism with 2 and 3 and get A, arrow, D, and not E. Now that doesn't actually match what I need here, but I'm one step away. So the hypothetical syllogism came in up here, and now this will be my line 5, and I'm just going to do another commutation on the consequent of line 4, changing the order of the conjunction there. Here now are the 10 replacement rules. Because these are based on truth functional equivalences, they're often also called equivalence rules. And because they allow you to replace or substitute parts of formulas for other parts of formulas, they're often also called substitution rules. Now we've seen commutation, and that's pretty simple and obvious. You're familiar with this from addition and multiplication in mathematics. The order of the components being operated on does not matter. And so in a derivation, we allow ourselves to change the syntax, to switch the order. Another one that you're probably familiar with is association. This is one where the placement of the parentheses around a three-part conjunction or a three-part disjunction doesn't actually matter. And so we are allowed to move those parentheses. See, this moves over to here. Similarly, you're also probably familiar with the notion of double negation. If you have a formula with two hooks on it, that's semantically equivalent to the formula with just a single hook, so one can be traded in or out for the other. You may remember from translations in Chapter 2 that a negated conjunction is equivalent to a disjunction of negated components. And similarly, the negated disjunction is equivalent to a conjunction of negated components. That is to say, not both P and Q is equivalent to either not P or not Q, and neither P nor Q is equivalent to both not P and not Q. Because of those equivalences, we allow ourselves to substitute, replace these equivalences in derivations. And we'll see how that can be useful in just a minute. Some of the other very useful ones are implication, which tells us that every conditional is equivalent to and replaceable by a disjunction where the antecedent gets a hook attached, or vice versa. Distribution of conjunction across disjunction or disjunction across conjunction, breaking the biconditional down into one of two equivalent, more complex statements. Transposition, which tells us that if we flip the order of a conditional, then negating each piece maintains equivalence, and so we can substitute the one for the other. There's also the exportation rule, which you may have talked about doing translations. A chain of conditionals with a complex consequent is equivalent to putting the two antecedents together in a conjunction. And last but not least is the idempotence rule, which tells us that any formula is equivalent to its redundant conjunction or redundant disjunction, or thinking right to left here, if you have a redundant disjunction or conjunction, it's going to be equivalent to and therefore replaceable by just the formula itself. Now, in the next video, we'll look at how to decide when and which of these rules to use. One of the great, but also sometimes frustrating things about SDE is that there's a lot of redundancy in the system now. And so there are going to be many different ways to efficiently complete a derivation. So two different students, or the same student at two different times, may come up with slightly different derivations by exploiting these rules in slightly different ways. How to navigate all that will be the subject of Chapter 4, Video 8, SDE Strategies. Let's take a look at one or two more examples. Let's take a look at another example. Here's a nice one. Not too simple, not too complicated. Our goal here is either not B or not A. Now, looking at the main connective there, it's the V, a disjunction. But if I remember the usefulness of my De Morgan's rule, I also see that if I could produce hook B wedge A, then my last step could be a De Morgan step, distributing that hook across the conjunction to get the disjunction of negations. That suggests that I want to get hook B wedge A. which is close to but not the same as the antecedent in line 1. Now I recall that one of our new rules, modus tollens, allows me to get the negation of the antecedent if I can have the negation of the consequent. Interestingly, the negation of the consequent would look like this. If I could get that, then I could use it with line 1 to get something close to my second to last line. But notice that line 3 is actually a form of line 2 according to, again, the De Morgan's rule. So we'll say we get to line 3 from 2 by De Morgan's. What's happening in line 2 is that we have a conjunction of negated pieces, and we're applying the rule in the right to left direction to get a negated disjunction. And remember, that's useful. And remember, that's useful because now 3 is the negation of the consequent of 1, which allows us to derive the negation of the antecedent of 1 with 1, 3 modus tollens. And how is that helpful? Well, all we need to do is apply good old commutation to line 4 and switch the interior of line 4 so that it gives us line 5. And then the last step is to distribute that hook across the conjunction. And that gives us hook B, V, hook A, either not B or not A, from 5 by De Morgan's. One of the initially intimidating things here is that we have a lot of choices. There are other ways to do this and other orders in which to do these lines. But by the same token, that gives you a lot of ways to discover a solution to the derivation. So again, I'll show one more example, and then in the next video, we'll talk about how to strategize these sorts of derivations. Now, here's a relatively simple derivation, although it would be very difficult without SDE. Without SDE, we would have to do 2 V eliminations with one inside the other, which takes a long time and gets pretty complicated. But there's a couple different ways we can do it here. Let's put our goal statement in. And we might say, let's do an arrow introduction. So that if we assume A, the antecedent of what we want, and can work our way to C, then we'll have the conditional we want. Now, there is a way to do this one without doing a subderivation, but let's look at this version first, because you don't have to avoid subderivations. If the subderivation approach in a particular derivation makes sense to you, then by all means use it. Now, I have something very close to a disjunctive syllogism here. But officially, in order to do a disjunctive syllogism, I need one of the 2 disjuncts with a hook attached. Since the left disjunct of line 1 already has a hook attached, I need hook A in order to apply disjunctive syllogism. But of course, with the double negation rule, I can get hook A from line 3 by double negation. That now gives me B from 1, 4 disjunctive syllogism. The rule doesn't appear on the screen here, but you can check. And now 2 and 5 are very close to allowing a disjunctive syllogism. But again, I need to create hook B from line 5, double negation, and then 6 and 2 will give me C by disjunctive syllogism. Then we can step out of the subderivation and cite 3 through 7 arrow introduction. Now we'll talk about double negation a little more in the next video. Here's a slightly different approach. One really useful rule is the implication rule, which allows you to switch back and forth between disjunctions and conditionals. What it tells us is that every conditional is equivalent to and therefore replaceable by a disjunction where the piece that was the antecedent has a hook attached. That's useful here in this way. Lines 1 and 2 look a lot like this, so we can change them to lines that look like that. So line 1, if we apply implication moving from right to left in the implication rule, gives us this. And line 2 gives us this. And you probably see that now we're nicely set up for a hypothetical syllogism with 3 and 4. Consequent of 3 matches the antecedent of 4, so the hypothetical syllogism connects them and drops the middle B out. Again, there are other ways to do this derivation. The power of SDE comes with multiple different approaches. And again, you don't always have to find the shortest approach. Our second derivation here is significantly shorter, but that doesn't really matter. If you figure it out in this form, that's just fine as well. Now, our next video will talk about how to strategize and how to pick from among these 10 rules and the 3 additional inference rules. One last point for this video. So if you remember back, our original system of 11 basic rules, SD, was all inference rules. To create SDE, we added 3 more inference rules. You can tell they're inference rules because you are always required to have whole lines of a certain shape as input that then allow you to get a single line of output from the rule. So all of the original 11 rules look like this. They go from the top of the page down to a result. And they are one-directional rules. The replacement rules, however, are bidirectional, and they're written across the page and can be read left to right or right to left. They can be applied left to right or right to left. So that's what we mean when we say that replacement rules are bidirectional, whereas equivalence rules are one-directional. The other major difference is that inference rules require us to match the formula on a given line exactly, the whole formula. So we can't apply modus tollens or hypothetical syllogism unless we have a line with conditional as the main operator and another line with the hook as the main operator. Or in the case over here, 2 lines each with conditional as the main operator. And of course, the other parts of the pattern have to match as well. But replacement rules require only that some component of a formula match the form in the rule. That's why when we start with something like
this, we can just alter the part inside the parentheses. So substitution rules allow us to work on parts of the lines, and that can be very powerful in more complicated derivations. Again, the details of this is something we'll go into more in depth in the next video.